and thank you all for attending this webinar session titled How Thermal Provides a Fast and Effective Solution to Eradicate Japanese Knotweed. I'm Aurélien Van Kerkhove, and I will be your host during this webinar session. I'm the team leader of the business development team of Amherst Technologies. Today, our guest of honor will be Lucie Deveau, who is a bioengineer, basically. She did her thesis in the phytoremediation and the phytomanagement. Since then, she had the wonderful idea to join Amherst Technologies. She worked on 2 different sites. The first part was as a project engineer. So she worked on some iconic projects as the remote flame we presented during our last webinar, and also highly contaminated sludges in Poland. It will be the topic of our webinar. And at the same time, she worked in the innovation team. She basically worked on a scaling up process on the Japanese knotweed. So Japanese knotweed with a kind of big social issue. Just if I take a look about my morning, I was cycling along the canal, and you can see along the canal a lot of Japanese knotweed. And when I arrived in the headquarters, just around our office, you can also see Japanese knotweed. So that's a big concern, a social concern. And so we have to address this issue with some innovative solution. And that's exactly why Lucie used this time to work on the scaling up process. Just before starting and to hand over the floor to Lucie, just to give you some practical there is some issue with the sound. No, the sound is okay. So just to give you some practical information before starting this webinar, the presentation will last around half hour. And then we'll jump to a Q&A session. So just please feel free to write all the comments during the presentation. And I will take a look just after. I will make sure that you receive an answer. After the webinar, you will receive by mail a certificate that attests your presence during this webinar. And you can also see this webinar on our YouTube channel, on our website. So I think we have all the information to start. So I will hand over the floor to Lucie, and that will reveal all the secrets she developed the last 2 years.
So thank you, Aurélien, and thank you for having me. And thank you, everybody, for being here today. So I'm going to directly dig into the subject of today, and I'm going to try to explain to you how thermal treatment provides a fast and effective solution to eradicate Japanese knotweed. First of all, I thought it was kind of important to have a background about our own company and what Amherst Technology does every day. Also, I thought it was really important to have a background about the Japanese knotweed itself, to better understand the plant, to better understand the issue. Then I will talk more about the neutralization solution and what we actually did in Amherst Technology to develop a thermal solution about it. So as you maybe know, Amherst Technology is a technology provider for soil remediation based in Brussels. It has been on the field for more than 25 years, and it's working worldwide now. We have our own manufacturing facility, and we also have our own research lab, because it allows ourselves to be always up to date about remediation issue. We have worked with a lot of people and a lot of partners. You can see on this slide that there is a lot of big companies like Eni or Total or Vinci and etc. We also have a lot of projects all over the world, like you can see on this map, mainly maybe in Europe, but we are spreading our activity every day. And so that's it. Like this, you know a little bit more about us, and you will understand why it was important to learn about us. So now I'm going to directly talk about the Japanese knotweed and more about the concept of invasive plants. So you have to understand what's an invasive plant to understand why the Japanese knotweed is an issue. So you have to know that the invasive plant, it's a not indigenous species, which means that it's a not local species. It's a species that we introduce in a new environment where it does not belong, and usually it's creating a lot of issue. It can be environment issue, economic issue, and also human health issue. Regarding the environment, it really attacks the biodiversity because it can really induce the disappearance of a lot of local species. I know that I think you know that usually when you lose a species, it can influence other species because simply by the fact that usually we eat plants or we eat other animals. If something is disappearing, we are lacking something in our food chain, and so it can induce a lot of really bad consequences for the entire biodiversity. And in fine, it could also be an issue for human health and human food security, for example. There is also another issue, it's more economical. So the Japanese knotweed and more the invasive plants can really spread everywhere. They don't have limits, they don't stop to crops, they don't stop to garden, they don't stop to sidewalk and everything. So it can create a lot of infrastructure damages, and so it can cost a lot to our society. And it could also really be an issue for food security again. So now that you understand a little bit more about what's the invasive plant, I'm going to talk more about the invasive plant in Europe. So you have to know that today we have made a list of 41 invasive plants that we are regulating and that we know about. You know that today in Belgium, we have 37 of these 41 plants in Belgium, so it's quite a lot. In this list, you can find aquatic plants, trees, grasses, climbing plants, and also other type of plants. And it's this type of plant that we are gonna be talking today because the Japanese knotweed belong to this kind of plants. So the Japanese knotweed itself is an herbaceous perennial plant, which means that it's a plant that grows all year long, which means that usually it's like growing during spring and summer, then die kind of during autumn and winter. It doesn't really die is the issue here. It was introduced around the 19th century because people thought that it was really a pretty plant. Also, it was really good for feeding the cattle and also the cows and everything. And it was also considered as a really good plant to have quality of nectar, and so really good for bees. Unfortunately, now we can really say that Japanese knotweed has been, for the last maybe 15 years, one of the most problematic plant species in the world. And the reason for that is because it's using a certain way to spread. And this way is the vegetative reproduction, which means that it doesn't especially need another plant to spread and to create another entity. And so to be more precise about the vegetative reproduction, so it's the capacity of a plant to create new entity from a fragment of itself or from a specialized reproductive structure that belongs to the parents. And in this case, the Japanese knotweed is using rhizome. So rhizome that you can, sorry, I have been a little bit fast. You can see on the two last picture that I just showed you. So the rhizome are underground horizontal stem. So they are storage body that have everything that a new plant needs. They have starches, protein, and other nutrients. So it's really like it's spreading underground. And then when it's ready, it's just creating a new plant that is genetically identical to the parents. So they are creating clones. So the reason why Japanese knotweed is quite complicated to get rid of, it's because of this rhizome that they are underground, and because it's really like it's storage body, but they are highly resistant. So as I said, Japanese knotweed is an invasive plant, so it induces the same problem of any invasive plant. It can threaten our biodiversity and also induce a lot of infrastructural damages. So it can break concrete, it can destabilize buildings and a lot of things. So the main thing to know about it, it's a plant that spreads quite fast. It can grow 10 centimeters a day. It has a really interesting rhizome network that can spread from 3 meters deep to 7 meters horizontally. So it's quite a lot of rhizomes surrounding one single plant initially. The rhizomes are really resistant to environment, to cold, heat, drought, and everything. It's also really resilient to cutting, thanks to the rhizome again. You can cut it, but it can regrowth because the rhizome are underground, so you're not cutting the rhizome. All these reasons are the reason why we need specialized naturalization solution. So it's the reason why I'm going to talk a little bit more about the naturalization solution that we are using already today to better understand the entire issue here. So the first one I'm going to talk is the chemical injection. Usually you inject herbicide like glyphosate or imazapyr in each of the stems that you before cut, and then you kind of let the plant do her thing. So usually the plant is like moving nutrients thanks to its roots and everything. So you do the same with the injection of the herbicide, and usually it works quite well. So there is a lot of positive facts about this technology, is that it doesn't impact any other plant species or any other species around, because before we were only spreading herbicide everywhere, which could attack a lot of different things. Here it's really targeting only the Japanese knotweed. And also, as we study better the plants, we really improve the way that the herbicide is like targeting rhizome. But the issue of this technology and this way to get rid of the Japanese knotweed, it's the risk of dormancy. So which means that if we miss one rhizome, it could make the eradication method unuseful, because there is only need one rhizome for the entire plant to regrow. Also, it's a technique that asks a lot of manpower, and usually it has many applications. It's not just one time you inject. Sometimes it doesn't work, so you have to repeat. But it's still really efficient, and it's usually the technique that we use today. Another one, it's simply excavation and landfill. So usually you just dig a huge hole where there is Japanese knotweed. You took everything to a landfill, and then it's going to be treated. The positive point of it is it's fast. It's really an eradication method if you're doing well. Before you do a study to know precisely where every rhizome is, there shouldn't be any regrowth if there is no rhizome. Unfortunately, the downside of it is that it's really labor intensive, so it can maybe kind of attack the soil. So it's not that great to move soil and to dig holes in it. It can be it can cost a lot of money, and also it's only moving the issue to other places, which can lead to other consequences, because if there is rhizome that just like fell on the road during transport, it could contaminate other places. And also you need to find a way to get rid of it when you're in the landfill. So it's still not a complete eradication method, complete. There is a lot of other methods that I'm not going to talk today, because I want to focus more about question and some of treatment, but there is also choking and other things that like this, So, sorry, I forgot one, which is interesting, is the biological control. So it's using simply like fungus, insects, or even animals that are living to kind of kill the plant itself. Usually you can find this species in the country where you found the plant, so here in Japan or East Asia. And so you simply have to introduce this living form into the milieu, and they are going to do the rest. So it's really interesting method, because you don't especially use chemical products to do anything. So it's interesting regarding the environment. And it's also really a specific technique. So it's targeting usually the plant that you want to get rid of. Unfortunately, it's quite a fragile technique, because when you're working with living forms, you have to be aware that a lot of things can happen. It can die, it can not appreciate the new milieu. There is a lot of things. So usually it takes a lot of time to develop, because you also have to be sure that what you introduce in a new ecosystem is not going to become invasive too. So it's really interesting technique, but sometimes it asks a lot of research, so it's kind of slow to produce. So then, now that you have all the backgrounds or the solution that already exists today, I think it's now time to speak about what we did and what thermal treatment could give to us to eradicate Japanese knotweed. So you have to know that we have a thermal desorption technique that we're going to use here in this case. So it's simply that thermal desorption technique consists of heating the soil that is usually contaminated. And then by conduction, the heat is transmitted to the ground and we evaporate the contaminant and then we take care of these vapors. Here in this case, we don't have an actual pollutant that we need to take care of. We just need to heat. So as you can see on the slide, it's simply a heating source that's creating hot gases that then are injected thanks to a tube inside the ground, and then the gases is going in outside. This is our technology that we call smart burners, and we kind of improve it a little bit to make a better energy consumption in this case. So we noticed that usually the hot flow that goes out of the burner, it's around 250 degrees, which was kind of a loss of energy and a lot of heat. So we are reusing this kind of heat inside another well that we did is the same. And so it allows us to reuse lost energy, to reduce fuel energy. So because you can here in this case use propane, fuel, or diesel, or I don't know, even electricity to do so. And also it allows us to increase the amount of soil that is heated by only one burner. So now that you have all the information about our own technology, I'm going to try to explain the way that we work for the last 2 years. So first of all, we work with a lot of people. So we work with the University of Leuven, with the Municipality of Heerlen, with Tamak Shift, and with Planten Gezondheid Dienst. Yeah, I think it was that, sorry. So we ask ourselves the same question that we put on the name of this webinar, say, how can we treat Japanese knotweed with thermal destruction or thermal treatment? So first of all, we thought it was necessary to better understand the thermal treatment on RHIZOME, because we learned, like, we read a lot of things about it, but we never practiced it. So we asked the University of Leuven to do some experiments on it. And then once we had all the information to do, we try on site to do tests. So we did an in-situ test and an ex-situ test. And then we really follow up about the regrowth, the possible regrowth of the plant to be sure that it works. So, sorry, right. With the university, we did different tests. So usually they were taking RHIZOME into an oven. They heat it up at many different temperatures, between 50 degrees and even higher temperature. And they changed the time of the cooking time, if you can say. And then they were taking the RHIZOME and they were putting it back in a greenhouse, and they were watching if there is any regrowth. So thanks to their study, we noticed that 50 degrees for 3 days in a row was enough to neutralize the RHIZOME of the Japanese knotweed. You have to know that the study was made between 33 days and 60 days. So we knew that after 33 days, there were no regrowth at this temperature and for this timing. So now that we had the target temperature to reach, we did the in-situ test in Heerlen, with the municipality that is located in the Netherlands. And we did a project that was in a quite populated neighborhood on the side of the sidewalk. Here we knew that the Japanese knotweed RHIZOME were mainly in the first 30 centimeters of soil, but we knew also that some RHIZOME were found deeper, up to 3.5 meters. So we decided for safety and to be sure to neutralize each RHIZOME to heat the ground up to 4 meters deep, sorry. And so the target was I say, 3 days at 50 degrees. So with this project, we decided to have 8 smart burners, and also we did 16 wells. Like I said just before, we have more wells than the number of burners because we reuse the hot flow to reduce our energy consumption. Then during the treatment, we follow up the temperature at different depth and also at different localization on the site. The treatment only took 10 to 15 days, which is quite fast. And the result is that since July 2022, it's when the test ended, we still have no regrowth on site because we are still following up, thanks to our partner, the regrowth of the Japanese knotweed there. And so it has been 8 months and we have nothing that grew back. And also, just to be sure, we also took sample at the end of the treatment and we gave them to the university and they redid a sample test under ideal condition and still no regrowth after 33 days. So it seemed that it worked. Another test that we did, it was inside a container. So we just put a soil with rhizome of Japanese knotweed inside an insulated container. We heat it up at the same target that we use in Ireland at 15 degrees for 3 days in a row. We follow up also the temperature at different depth and also at different distance from the eating source, just to be sure that the temperature was homogeneous inside of the container. So the treatment here was only 7.5 days. And again, same results as in Ireland. We have no regrowth after 33 days of follow-up. So now that you have all of it, we can definitely conclude a lot of things. So first, we can say that Japanese knotweed is an issue. Like, I think we cannot go against this conclusion. It creates a lot of problems regarding building stability, but also it's really a threat to our biodiversity. We can also say that thermal treatment actually works. Because we have seen it on like in different studies, in our own studies. So definitely it could be an interesting method to use now to eradicate Japanese knotweed. We also discovered that 50 degrees was already enough to neutralize Japanese knotweed. And so it's quite interesting regarding the energy consumption because it's quite low temperature, especially for thermal treatment. We are more used to go up to 100 or even higher. So it's kind of interesting in this case. We can also say that our technology can definitely be flexible and adapt to this kind of treatment, which is really interesting for us, obviously. And we can also, and I think it will be my last word for today, to say that thermal treatment, it's quite a fast treatment and should be considered today as an interesting method to eradicate Japanese knotweed. So that's the end of my presentation today. So if you have any questions, do not hesitate to ask them in the chat. Thank you for listening.
Well, thank you very much, Lucy, for this very interesting presentation. I really like the scaling up process, and also because I'm a chemist, just the introduction about all the invasive plants, and I really love the way you presented this one. I saw a comment coming, so maybe if I can just have a look on the conversation. Perfect. All right, so the sound is gone. No, it's there. Next question. Burners were placed in the unsaturated zone. So for the project in Ireland, so do we know exactly if we were only treating the valuable zone, the capillarity zone, or also the unsaturated zone?
No, it was only the unsaturated zone, I think. Yeah, I don't recall that we had water in it or any issue of it. Yeah.
Yeah, and just I will also give some more information about this one, but more chemically speaking, it's just heating up a soil up to 50 degrees. If it's the saturated zone or the unsaturated zone, it will, I would say, in terms of energy consumption, it will be almost the same. Mm-hmm. So Ambrose Technologies intervenes after the characterization, but basically in terms of fuel consumption, that's exactly the same to treat both parts. I have also a few more questions. You were maybe a first question. It was a slide 12. It was about so Japanese knotweed can cause a lot of damages for the buildings and can create some structural damages. And my question was like, would it be an issue to treat it just near to the building, and maybe I don't know if it's possible, but to have the roots under the building?
Personally, I don't think it's an issue, because with Armor's technology, we have done a lot of projects under buildings, especially in Brussels, because we have a lot of buildings and a lot of pollution underground. So it's a really adaptive method and a solution. So it can be done because it's, I don't know how to say, it's quite a flexible technology. So as you can say, really.
Okay. That's quite clear. Also, at the beginning of the presentation, you were talking about all the invasive plants in Europe, and it's like, okay, we took one of the 41, if I remember well. So have you already thought, or maybe just started, investigated some thermal treatment on other invasive plants?
So we kind of looked it up a little bit. We didn't do a big investigation, but we really think that if we can treat Japanese knotweed rhizome, it could work on other plants that have also rhizomes. So it could be an interesting study to do further in time. But I think definitely we have to do again research to see if the rhizome react the same way that the Japanese knotweed rhizome. But I don't see any reason why it will not work on other invasive plants that have rhizome network.
Okay, very interesting.
Yeah.
I look forward to getting some new information about this one. Also, Armor's technology basically intervenes after the characterization. So I will just do a kind of quick game, but you receive a call, and in this call, someone is saying, "Oh, we have I would say kind of contamination with Japanese knotweed, but it's only shallow, just 20, 30 centimeters." If just I take a look back on the presentation in Ireland, you use some vertical heating tubes, but in these specific cases, it doesn't make any sense to use heating tubes of 20 centimeters, and you have the above ground part of 1 meter. So what could you recommend about this kind of shallow contamination?
So yeah, if there is only rhizome just underground, like in the first 30 centimeters of soil, it's not really useful to dig a huge hole for. It's not necessary. So for this reason, I think what could be interesting is maybe excavate it, because it's not a lot of soil, and then doing like we did ex situ, using a container or something else, still using thermal treatment. Or even I think we could, I don't know, dig trenches or other things. We could really adapt, I think, our own technology, because there is no reason why we couldn't. It's really flexible.
Okay. I just saw new questions in the comments. So it's the question is 3 days at 50 degrees is enough. So the shortest treatment shown is 7.5 days. So does that mean it takes 4.5 days to reach 50 degrees in the soil?
Yeah, definitely. Because we need to stay 3 days in a row at this temperature. So obviously the temperature will maybe go higher, but we took 4.5 days to reach 50, and then we had to wait 3 days just to be sure that everything was naturalized.
Okay. So it also means, so it's kind of 10 degrees per day, maybe 15 degrees per day?
Kind of, yeah.
Okay.
Definitely.
And the last question I have, I don't know if you have other question, but that's because basically that's all the same questions we can receive it, but would you have a price to share about this kind of remediation?
Yeah, the thing is, like, a price of a project depends about a lot of things. It depends about the quantity of soil that need to be treated. It depends on the accessibility of the site. It depends on the fuel use, if it's electricity, propane. Like, we know that it can, like, the course of it can change a lot. It depends about the time that has the client itself. So for an easy project, it could be between 20 euros per ton, but we know that usually it can be a smaller project, and I think so it could maybe reach 50 euros per ton, but usually it's between 20 and 50. So
okay, it depends on the parameters, basically between 20 and 50 euros per ton. Okay. Okay. So we have a new questions here. What are the advantages of doing a treatment in a container compared to an iced tea?
It really depends on what you want to do and what kind of site you have. If you have a site that you cannot really access, and it's quite hard to do a nice TD, but it's easier to excavate it and then treat it. So it would be better to use the STD way to do it. But also, usually it's maybe better to do a nice TD and so to stay on site because you don't have to move any soil, which is always better because you have less impact on the environment itself. So it really depends on what kind of like issue you have and what you have to work with what you have. So I will not say there is more advantages or not. The only one I see it's really because you don't have to move soil, so it's maybe better to stay where you are and directly treat it, and it's less disruptive. But if you can, it's always better to do an HTD still.
Okay, that's quite interesting. I don't know if you have other questions. I cannot see. Oh, Colin has questions. Do you get the same results eating the ground with steam? So it's kind of quite a wide question, but
good question. I think like I think we should have the same result because it's really the temperature that's really making the process. But I will never try it, so I will not say more about it. But if you reach 50 degrees for 3 days, there is no reason that you don't have the same results. But
okay,
it has to be tried.
Maybe if I can also add a comment about what you just said, is working with steam is basically also working with the heterogeneity of the soil. So working with steam or working with by conduction with hot air could be the same if at the end we have a homogeneous soil. But what's happening when basically you have different, I would say, you have a kind of complex lithology into the soil. So we have a sand and gravel at the top, and we have maybe clay just before. And so at the circulation of the steam will be better on the top, but it will be more complicated at the bottom. So it's like you will get more uncertainties, and especially when you are working with in situ, because you have to deal with the uncertainties there. So I don't know if you have other questions. So I think it's the right time to thank you all once again for attending this meeting. Thank you very much, Lucy, for this really wonderful presentation. I really hope you will get the energy to do another presentation there. And our next monthly webinar will be about the follow-up we can do remotely just to control our burners and also to follow up the temperature, the pressure, just to control it remotely. So thank you all, and I wish you a good lunch.
Yeah. Do you know the time? Yeah.
Okay.